Good morning to all. I welcome everyone to the third day of the GION-sponsored workshop titled Advances in Biofuel and Bioenergy Research. Now I will invite Dr. Ramraj Bhupati sir to take over the session on the topic Biorefinery Concept.
All right. Good morning. We're going to continue on the topic of yesterday and last 2 days we talked about bioethanol and anaerobic digestion for methane production. Today we're going to talk about the concept of biorefineries. So in biorefineries we want to use everything, nothing going to waste. We want to find value-added product. So we'll look at for ethanol, from biodiesel, for anaerobic digestion, what are the various feedstock out there, how to calculate tonnage, how to calculate sugar production, ethanol production. I'm going to go through a little more math involved. We're going to go through step by step. Okay? So the talk is like go through some background, what is refinery and biorefinery, talk about sugar and molasses ethanol biorefinery, starch ethanol biorefinery, oil biodiesel biorefinery, and last anaerobic digestion biorefinery. Okay. So just go over again. So 1,500 years ago, the world population was 150 million. Most of the population were located right in India and China and Western Europe. You don't see nothing at all here, right? So later on, migration started and population exploded. Now we are reaching 8 billion, close to 10 billion by 2050, right? So that's the scenario we are having. We have problem of energy, food security, and the environmental degradation because of population explosion, increasing demand for resources, for food, feed, energy, also generating large amount of waste, wastewater, everything going to the environment, degrading the environment. And then we have the, of course, greenhouse gas emission. We are all witnessing warm climate and global impact on that, right? So if you look at that again, go through the same slide. The very first day I talked about the monitoring of CO2 in the atmosphere started a long time ago. It was around 300 ppm. It went up to recently all the way to 415 ppm of CO2. Keeps increasing every year because of human activity. And you can see global energy-related carbon dioxide emission from 2019, it's around 33 gigaton of CO2 we are putting in, lots and lots of CO2. The consequences of that is you have polar melting, polar caps are melting, sea level rise and flooding, and erosion of land from coastal intrusion. All that is happening because of global climate change. Okay. This is just to show you again, when you shut down human activities, you'll see that immediate effect of CO2 in the atmosphere going down. That happened in around COVID time, and that is an evidence-based data to show, yes, it is human-related activity that is causing CO2. So let's talk about refinery and biorefinery. Okay, if a concept of petroleum refinery is an industrial facility consists of a group of unit process and operations based on crude oil, right? So we're getting crude oil, petroleum, and we are refining the petroleum to various products such as gasoline, diesel fuel, jet fuel, tar, heating oil, kerosene, and LPG, liquid petroleum gas. So thus refinery produce multiple fuels, multiple product to maximize the output, and you close the loop. You don't see anything going to waste, but when you use those energy, you get the CO2. But when they are producing everything out of the oil, lot of product they are making. Okay. So how they are doing it? They are doing it, and if you look at the design, the distillation tower. You have the residual, we have, a lot of these the cracking of that, you get your gas, oil, medium weight gas oil, diesel fuel, kerosene, naphthalene. As it goes in lighter chain, it goes up. And by doing this process of various cracking, alkylation, and reformation, you can make a lot of this product. You can see the end product like asphalt base for making your roads, industrial fuel, diesel fuel, jet fuel, all the way to LPG. All right? So this is what biorefinery concept is. Getting one feedstock, in this case petroleum crude oil, making multiple product, right, for a lot of different purposes. The same concept can be applied to biomass. Okay, that's what we call that biorefinery, biological based refinery. Okay, same concept we are trying to adapt. So if you look at biorefinery definition, what is biorefinery? That's what in the U.S. National Renewable Energy Laboratory defined biorefinery as this. A biorefinery is a facility that integrates biomass conversion process and equipment to produce fuels and chemicals from biomass. Okay? The biorefinery concept is analogous to petroleum refinery, similar to petroleum refinery. Industrial biorefineries have been identified as the most promising route to the creation of new domestic bio-based industries. Okay, so it creates a lot of jobs, creates a lot of new industries. By producing multiple products, a biorefinery can take advantage of the differences in the biomass components, variation in the feedstock and intermediates, and maximize the value derived from the biomass feedstock while also being able to adapt to changing market conditions. Okay? So the high value product enhances profitability, while the high volume fuel helps meet national energy needs. So that is a lot of things to digest. All right, that's what the biorefinery is. To put it in simple terms, you make many product, and many product has flexibility, so you can change the product depending on the market needs. So that's called biorefinery. We make multiple products from one feedstock. That's called biorefinery. Okay. So let's look at how this works. Okay, here's your crops from sugarcane, sweet sorghum, cassava, corn, all the way to these energy crops, and then we have the oil-based crop like soybean, sunflower, palm oil. From those sugarcane and sweet sorghum, it makes sugar. Sugar is directly going to fermentation, and then they go to make ethanol. Okay, and when you have starch, you need to do hydrolyze them by putting amylase, make your sugar, and then goes to fermentation, you make ethanol. When you have fiber-based crops, lignocellulosic, it has to go through pre-treatment, and pre-treatment go through hydrolysis, get your sugar going through fermentation, or you go to thermochemical route, gasification, pyrolysis, combustion, you burn them, and then get your syngas and other product, and those product can go straight into your different product that you can make. So you can burn them to make electricity or heat, and you make other fuels and chemicals from this product that comes out. And then if you look at oil-based crop, you take oil and do transesterification reaction. We talked about yesterday, you get your biodiesel. And then you can, from a waste cooking oil from restaurant and other places, you can use the waste oil and make transesterification, you make biodiesel. So you can see various crops, you can see the intermediate products, what the technology is used, conversion technology, and you have the final product that you can see. That's a concept of biorefinery from biomass, from various crops. Okay? So let's talk about the methanotrophic bacteria is the one kind of bacteria that can use methane as a carbon source. So methane produced from anaerobic digester can be used to grow this bacteria, and then bacteria can make your polyhydroxy butyrate acetate, single cell protein, methanol, a lot of different products the bacteria will make. Okay, so here is the concept of that. So you have your anaerobic digester. The product of the anaerobic digester is methane and hydrogen CO2, and you can use that to make a secondary product, and you can also use methanotropic bacteria to make this product, and also other things that you can make from this product to make heat, electricity, hydrogen, diesel fuel, all that stuff you can do that. Okay. And if you look at lignocellulosic biomass, same concept we went through, pre-treatment, hydrolysis, you get your polymer cellulose, hemicellulose, lignin. The sugar goes to enzymatic hydrolysis, fermentation. You make variety of product from not only ethanol, butanol, lactic acid, levulinic acid, furfural, 5-hydroxymethyl furfural, DMF. Lot of product you can make. Once you get the sugar, it's a sugar platform. Sugar is your feedstock. Okay. And then lignin, you get lignin, you can go through thermochemical route. So lignin is really hard for fermentation. You cannot use lignin for fermentation. So the phenolic compounds could be used for resin, adhesive, and other fuel additives. Okay. And if you use the liquefaction process, where the bio oil, bio crude, you go through separation and upgrading by cracking and hydro treatment, you make a surfactant and other product. Okay. So that's one concept of biorefinery, from anaerobic digester, from lignocellulosic biomass, and oil-based crop. You can make a variety of product. Look at the diversity of product we have. You can make a lot of things, okay? And we can also, if you are really good, if a company is really good, they can produce according to the market needs. If ethanol price is high, ethanol is in high demand, you make ethanol. And if you want more lactic acid, you switch to lactic acid. So based on what the market demands, you can modify your feed, and then you get your final product. You make money out of that, profit. So why biofuels, bioethanol, biodiesel? Why do you need that? Ethanol can substitute toxic additives that we mandate in the U.S. Before ethanol, the gasoline additive was this compound, very toxic compound called tetraethyl lead, and that was replaced by MTBE, which is methyl tertiary butyl ether, which basically oxygenate your gasoline. It burns better because it has oxygen in its structure. So your tailpipe emission have less pollution. Okay, that is the concept of adding blended product in your gasoline. So before ethanol was used, those chemicals were used. Those are known carcinogen, and they're really, really bad chemicals. They contaminated U.S. a lot of places. The storage tank leaked into the groundwater. A lot of people got sick from it. That's why they switched to ethanol. Ethanol does the same properties of oxygenated fuel, because ethanol has oxygen in it, right? So that's how the ethanol came into the fuel industry. Okay, they're replacing the oxygenated additive to your gasoline. So it improves fuel combustion. When you add to the gasoline, your tailpipe emission is low. Your carbon monoxide and other nitrous oxide are less when you have ethanol blend in your gasoline. So that is the impetus of why ethanol was get into the fuel industry, is as a blended agent to replace the toxic chemicals. Okay. So this is just to show every product we get in the U.S. is all blended with ethanol nowadays. So bioethanol, if you have a E10, 10% ethanol in your car, you don't have to modify the engine. The regular engine, gasoline engine, can take E10 without any problem, right? As you blend goes up, you got to have some modification to the engine, right? You can have E85 car, which is what Brazil mandate, 85% ethanol in your car, okay? Ethanol vehicle gives same power, acceleration, payload, cruise speed compared to gasoline fueled car. There is no difference in the performance, okay? There is in the internet, there is some people, say ethanol is bad for engine. That's not true. There is no scientific evidence for that, okay? Biodiesel can be used to unmodified diesel engine, because the diesel engine was first invented by Rudolf Diesel. What was the feed for the diesel? Anybody? The first diesel engine is your oil that you use for cooking. Okay, that was the first diesel engine run by Rudolf Diesel, right? And then petroleum came, replaced it. Okay, now we're going back to oil-based diesel engine. So biodiesel, the diesel engine can take your biodiesel without any modification. Okay, so it has high C10 number and comparable fuel property with that of a regular diesel. There is no change in the performance with the gasoline-based diesel and biodiesel, exactly the same performance. So let's look at some sugar-based feedstock. So the major ones are sugarcane, sugar beet, sweet sorghum. Those are the ones that produce a lot of sugar directly from the crop. And these are called sugar-based feedstock. These are efficient converter of solar energy. They harvest sunlight and convert them to carbohydrate in the form of sugar. In sugarcane, it is sucrose. Okay, 90% is sucrose. So these three feedstocks are called sugar-based feedstock. It's really widely produced all over the world. Okay. So let's talk about sugarcane. Sugarcane is a perennial crop. You put them in the ground, you can keep it cut for 4 or 5 years, and it comes back again and again, and then you replow it and then go back after 5 years. You can put new sugarcane back into the ground. So mostly cultivated in tropical, subtropical regions, account for 84% of the world sugar crop. Juice of the sugar cane contains 12 to 17% of fermentable sugar. 90% of that is sucrose. 10% is glucose and fructose. Sucrose is glucose and fructose, right? So 10% is the glucose. The main feedstock for bioethanol production is in the Brazil is the sugar cane, right? Brazil is the number 2 ethanol producer in the world. US is number 1. US use corn as a feedstock. Brazil uses sugar cane as their feedstock. Okay, so these are the top 2 ethanol producers in the world. The second crop is sugar beet. The sugar beet provides 16% of the world sugar production comes from sugar beet. Mostly grown in temperate countries like Western European countries, Northern Hemisphere countries. It's a biennial crop. You can grow 2 times a year. Okay, but for sugar production, beets are harvested annually, so leave it for the whole year. Okay. Fresh sugarcane beet contains 15% sugar. Okay, it has also a lot of sugar. So let's calculate ethanol production from these 2 crops. Okay, so ethanol in the US we go with gallon. Here in British units we use a liter. So I have the calculation for both liter and gallon. Okay, so the weight of the sugar cane times 0.5 by 6.7. The assumption here is based on research. 1 pound of sugar can make half a pound of ethanol. Okay, which is, if you convert them to kilogram, 1 kilogram sugar can make half a kilogram of ethanol. 1 gallon ethanol is 6.7 pounds. Okay, so that's a weight equivalent. So if you plug in these numbers, how much ethanol you can make from 1 gallon ethanol, 6.7 pounds of it. Okay, in terms of kilogram, it is 0.8. 1 liter equals to 0.8 kilogram. So let's talk about a question of how many gallons of ethanol we can make from 4.1 tons of sugar produced. Okay, if a farmer produces 4.1 ton of sugar, how much ethanol you can make? Okay, so ethanol, so 4.1 times 2,000, which is 2,000 pounds equals 1 ton, right? When you compute that with 0.5 divided by 6.7, which is the yield. So you can make 612 gallons of ethanol. So ethanol equals weight by sugar, and you convert them to liter. You can produce 2,325 liters of ethanol from 4.1 tons of sugar. Okay, is a calculation based on fermentation reaction and yield of sugar. Okay, so that's how much you can make from roughly 4 tons of sugar. You can make 2,300 liters of ethanol. Okay. So let's look at sugar-based feedstock. We have the sugar yield from sugarcane. You can 4.1 ton comes from per acre. Okay, so 4.1 ton is per acre of sugar cane harvested. Ethanol yield is 612 gallons. Okay, and in sugar beet, if you do the same calculation, it's 3 tons per acre. You can make 448 gallons of ethanol. Okay, so that's per acre of crop. How you're making, how much ethanol you're making. Okay. So sugarcane molasses ethanol biorefinery. Let's talk about this concept. So sugarcane is mechanically pressed. Once it's harvested, goes to the sugar factory, and they crush them, get the juice out of them. Right, just go through the crushing and all the juice comes out, sugar-rich juice. The sugarcane is primarily C12 because it's sucrose. Yeast is that we use for fermentation is Saccharomyces cerevisiae. That's the yeast we use to ferment sucrose to ethanol. Ethanol is recovered by distillation. Molasses is a major byproduct, which a very thick syrup comes out of that. Molasses contains 49% of sucrose, lot of sugar in molasses. Okay, so byproduct residue includes bagasse, molasses, vinasse, which is a liquid that comes out, and carbon dioxide. So those are all the product come out sugar factory. Okay, as a biorefinery, you don't want to waste any of them. You want to use everything that comes out of that. Okay, let's look at that concept here. So let's look at the whole unit operation here. So sugarcane is harvested, go to the factory, crushing, you get the juice out, go through the clarifier, and you get the sugar to the fermentation process. You can make whatever product you want to make. You can make beer, you can make ethanol, and then the other product that comes out is CO2, and then we have the when you distillate it and you dehydrate it, and that goes to 200 proof ethanol. This is what goes in your car. So people won't drink that. We add 5% gasoline to that to make it that you don't drink. And then the vinasse comes out as a effluent from the sugar factory. And then when you process the crushed sugar, dried one, we call that bagasse. Okay. So if you look at bagasse, there's a 40% moisture in it. You can dry bagasse and make a lot of paper product out of that. So sucrose is C12H22O11. With water, you make 2 glucose molecules. So sucrose is basically glucose and fructose. So from 2 glucose molecule, you can make 4 ethanol molecule and 4 CO2 from this process. Okay. So let's look at the concept of biorefinery here. So you have the sugarcane, whether it's sugarcane or sugar beet, go through the same process of crushing, getting your sugar extracted, go through molasses, fermentation, you get distillation, dehydration, and you get denatured ethanol by adding gasoline to it, and then give vinasse. Okay, this is exactly the same for your sugar beet process. Okay. So these are the product that comes out, the waste water that contains a lot of sugar in it, and this is how the waste product look like when it comes out of the sugar factory: molasses, vinasse, and bagasse. Okay, so that's your bagasse. When you crush and dry it, These are the byproduct you get. So bagasse is fibrous residue remains after sugarcane juice is extracted. If in the US you'll see big mound of this bagasse next to the factory. Okay, we have 1 metric ton of sugarcane can produce 140 kilogram of bagasse when you process it. Typically, bagasse is used for production of steam and generation of electricity. They use back in the factory as a furnace fuel for heating purpose. Even with that, there is a lot of leftover bagasse in there. Okay? Bagasse can be also used to make paper, pulp, acoustic boards, ceiling tiles, pressed wood, and animal feed. So a lot of use for bagasse. Okay? Vinasse is the liquid waste come out of sugarcane factory. It's a liquid fermentation byproduct following ethanol recovery. Is around 16.3 gallon vinasse per gallon of ethanol produced. Okay, a lot of water in it. So 16.3 gallon of vinasse is produced for every gallon of ethanol. So generally, in Brazil they use it as a fertilizer. They put that back into the ground. But you can get sugar out of that. You can extract sugar out of that. There's a lot of sugar in that vinasse. So that's how it looks like. Vinasse is applied back into the soil as a soil conditioner in Brazil. CO2 is, you make 4 CO2 from the sugar molecule. So a lot of CO2 is coming out. CO2 is a major byproduct of fermentation. Stoichiometrically, 4 moles of CO2 is produced from each mole of sucrose. As a conversion, if you convert them, you can make 466.7 kilogram of CO2 per ton of sucrose fermented in the factory. Okay? So CO2 can be captured and refined for use in carbonated beverages, the soda that you drink, and also you can make dry ice. Okay? So now we found out from everything that come out of the sugar factory, we have a use for it. Right? So make your main product of sugar, and then ethanol, bagasse, and vinasse, and carbon dioxide. Okay? So that is biorefinery. Nothing is wasted. You find product from everything that is come out of the sugar cane. Okay? So also you can use CO2 to make algae. Okay? So you can pump that CO2 come out of the factory, make an algal pond, produce a lot of algae as a feedstock, CO2 as a feedstock. So look at the mass balance. So if you have sugarcane, 1 metric ton, and when you crush and juice, you get 740 kilogram of juice that contains 135 kilogram of sucrose, and it has 605 kilogram of water. Okay? And then you do the fermentation, you make 55 to 60 kilogram of carbon dioxide, 550 to 600 liter of vinasse, 260 kilogram of bagasse with moisture, and then when you dry them, it's be 130 to 140 kilogram of dry matter bagasse. Okay? So that's the mass balance. From 1 metric ton of sugar cane, you make so much if you put them all together, it should come to 1 metric ton. Okay? That's what you're making. Okay? So each metric ton of harvested sugar cane yields 740 kilogram juice, 230 kilogram moist bagasse, or 130-40 kilogram of dry bagasse, 70 liter of ethanol, 550 to 600 liter of vinasse, and then 55 to 60. That's your mass balance calculations of 1 metric ton of sugar cane come out of the farm. Okay? So let's look at starch-based feedstock, switching to different crop. So these are commonly grown as food and feed supply. They include cereal like corn, sorghum, millet, wheat, oat, barley. These are rich in starch, these crops. It also includes cassava, potato, yam, and taro are a lot for 100% starch. Okay? The global production of starch-based feedstock is about 3.07 billion metric tons per year. Lot of starch-based products are produced. Cereal is 2.35 billion metric ton. Okay, the starchy roots have 0.72 billion metric tons per year you can make from the root. Okay, about 79% of used food feed application and 6% of for biofuel production is going. So 79% is going for it's a food crop for people to eat, and 6% of this we can goes to biofuel production for making ethanol. Okay. Let's talk about corn. Another feedstock. Corn contains 70 to 75% starch. About 98% starch-based bioethanol is produced from corn starch. In the U.S., the feedstock for ethanol is corn. Okay, about 40% of corn is used for bioethanol in the U.S. In Germany, they don't let the corn to grow mature. They harvest them before you have a matured corn. The whole plant is used to make ethanol. Lignocellulosic and not matured corn is used to make ethanol. Cassava, common in India and also other countries, Thailand, Nigeria, Indonesia, and Congo. So cassava root contains about 86% on dry white basis of starch. Okay, a lot of starch in, we call it tapioca cassava. Okay, it's a lot of starch in it. Okay. Let's look at ethanol estimate from both starch and grain. So the weight of grain per pound, divide that 56, that's a yield. Okay, 1 bushel, in the US we call bushel, 1 bushel is 56 pounds. Okay, so 1 bushel of corn you can make 2.8 gallons of ethanol, okay, which is 3.785 liters of ethanol. So that's the calculation based on research. Okay, so if you whatever weight you produce, you multiply by this factor, you know how much ethanol you can make. Okay. So here's an example based on that calculation. So how many gallons of ethanol you can make from 2.6 ton of corn? If per acre you can make 2.6 ton of corn. Ethanol in gallons is 2.6 times 2,000. The 2,000 is 2,000 pound equal 1 ton, metric ton. And you plug in this, you can make 260 gallons of ethanol, or and multiply by for the liter conversion, you can make 985 liter of ethanol from 2.6 tons of corn per acre that you produce. Okay, so just calculating based on farm yield, you can estimate before you harvest them. You know, based on this calculation, you can estimate what's the margin, profit margin going to be. Okay. Let's look at more details about starch in ethanol biorefinery. Look at the corn crop. The corn, if you look at the corn itself, it has an endosperm, pericarp, germ, and tip cap. And we did the analysis of in every part of the corn. You can see the corn kernel, what it contains: starch, protein, oil, ash, sugar. Now, in endosperm and tip of this corn, you can see this mass balance, how much of starch is there. There's a lot of starch in every part of the corn. So you can the whole corn for your ethanol production. Okay, is really a good feedstock for making ethanol. So starch ethanol biorefinery, two type of processing. We have a wet mill and dry mill processing. So in the wet mill, it's usually very large production facilities, 100 to 200 million gallon per year production. Very costly, a lot of investment at the beginning. You have to construct big plants. They can make multiple product. You can make high fructose corn syrup, which is in everything you drink, corn oil, ethanol, starch. We can produce corn gluten meal, corn gluten feed, and others. So those are the products that come out of the wet mill process. Dry mill is a small unit, not a big factory. Usually it produces 50 million gallons per year. and it's a less costly, small investment. You only make small product is not many products you make. You focus on ethanol and then the byproduct, the dry distillate grain with soluble, which is animal feed, is rich in protein for giving to animals. So those are two types of processing of starch ethanol biorefinery. So let's look at the wet corn mill processing, how it is processed. So corn is conveyed to large tank called steep tanks, where it is soaked for 30 to 50 hours at 120 to 130 degree Fahrenheit, around 55 degrees centigrade, in a dilute sulfur dioxide solution. Basically, you're cooking and getting the starch out. Okay, that's all you're doing. Okay, so that's the process. Looks like this. You get your corn and put in a big thing and start cooking, and you get your starch out. The starch go to the fermentation process. You make your ethanol and other fine chemicals, and you can also make syrup, and you refine the syrup. It's full of sugar, and the corn syrup and high fructose corn syrup is your product. And then you dry them, you can make starch. Starch is a product you can buy. Dry starch powder you can buy for a lot of cooking, right? And then you have when you grind and screen, you can make your germ separation. The germs comes and you use the oil refinery, you make your corn oil as a product you can buy, right, for cooking purpose. And then you get your fiber and separation. The fiber goes to your feed product with wet feed, and that could be used again. So if you look at this whole process, you make a lot of product, nothing is going to waste in this biorefinery concept. Okay? So let's look at some of the calculation. The average yield per bushel, so 1 bushel is 56 pounds or 25 kilograms. So that's what average yield look like. So starch, you get 31 pounds, 14 kilogram you make from average yield of bushel. You can make 12 pounds of gluten feed, 2.5 pounds of gluten feed, 2.5 pounds of gluten meal, and 1.6 pounds of corn oil from this process. Okay? So that's how it looks like when you go to the factory, the unit operation look like. Okay? So the corn comes in, goes through this liquefaction, saccharification, fermentation unit, distillation, get your ethanol and get your dry distillate for your protein soluble for animal feed, and then you go through secondary liquefaction process, you get other byproduct out. So that's your whole operation unit, and every step of the way you add enzyme to get starch hydrolyzed to make your sugar, and you add yeast to make your fermentation, and goes through fermentation tank, and then separation process, you get your alcohol out of the process. Okay, that's how it looks like in factory. So let's look at dry mill process. In dry mill process, looks like this. They only have two products, ethanol and your DGGS. So in dry mill process, you put 1 bushel of corn that goes into this process. Same process of slurry tank. You add this enzyme alpha amylase and glutamylase that break down the starch into sugar, goes to the fermentation tank, and then you make your alcohol, goes to the distillation, and get your distillation, make your ethanol, and then you have the waste product that comes out. That could be used for your DGGS product for your animal feed. Okay, so only 2 products out of this dry mill process is a smaller unit. There are not multiple products are made here. Okay. So in terms of calculation of how much you make, from 1 bushel at 25 kilograms, you can make 16 to 17 pounds of your CO2, 2.7, 2.8 gallons of ethanol, 17 to 18 pounds of your dry feed for your animal feed stock, and you have this 13 to 16 gallon of ethanol. So that's your end product of your from 1 bushel of dry mill process. So that's the structure of corn, why we need to add 2 enzymes to get your sugar. So because the corn starch is put together by alpha 1,4 linkage of all the glucose units are put together by this bond, and then the branched molecules are put together by this 1,4,6 D-glucose branch point. That's a different bond. That's why you need to add 2 enzymes to break this to release your sugar. Okay, that's a structure of your starch in the corn. That's how it looks like, chemical structure. Okay. That's why you need alpha amylase and glucoamylase. Alpha amylase break down the alpha 1,4 linkage. Glucoamylase break down this branched bond, so you can get all the glucose out. So average yield per bushel of corn in dry mill process, to sum up in this part, from corn price is $3.3 per bushel. Ethanol you can make 2.6 to 2 gallon from 1 bushel. You make $1.28 per gallon of ethanol. And the animal feed comes out of it. You can make 17 to 18 pounds of it. It's really high cost. $130 to $140 per dry ton. So that goes to cattle farms. Then you make 16 to 17 pounds of CO2. So that how much energy is needed to produce a gallon of ethanol, that's what the calculation. So you can convert that into dollar figure. Okay. So that's how it looks like, the dry distillate grind that goes into the cattle farm. So let's look at cellulose-based feedstock. Only look at lignocellulosic. And we have a lot of feedstock here. The feedstocks are switchgrass, napier grass, energy cane, poplar tree, eucalyptus tree, cornstalk, wheat stalk, straw, rice straw, a lot of stuff, wood chips from forest industry. All of them are potential feedstock for lignocellulosic ethanol production. Okay? So we went through that day before yesterday. That's the structure of plant made up of cellulose, hemicellulose, lignin. Lignin is polyphenol. We don't use it for fermentation. The cellulose and hemicellulose are made up of sugar. That's what that goes to ethanol production. This is how put together. The lignin is made up of polyphenolic compound. We went through this the other day. Okay? So the sugar is these 2 molecules. Okay? Hexoses, pentoses from hemicellulose and glucose from your cellulose. Okay? So if you look at how this molecule is put together in plant, it's look like a, if you want to visualize it, it's like a reinforced concrete. When you build a tall building, so this is what you put to reinforce a building, make a building strong. You have these bars and you reinforce with concrete in between. Same thing, that the plant is exactly like that. So you have this cellulose, that pillar, then you have this hemicellulose, this red one with the fibril, and this blue wraparound is your lignin, right? Is the same model is what your plant is made up of. It's a very strong polymer, natural polymer. Okay? These are the energy crop. They grow really, really tall. Right? These guys are 6 feet tall. You can see the grass that's growing. So these are very, very good energy crop. It doesn't need fertilizer. It doesn't need anything. It grow anywhere, everywhere. It not compete for your food production. A marginal land, not in agricultural land, you can make these crops. That's your poplar tree, and then your eucalyptus tree you're familiar with, is like common here. So these are tall trees, very potentially could be used for feedstock. So let's look at the yield of this. So the switchgrass, you can make 6 ton per acre if you plant it. Napier grass, you can make 20 ton per acre. Poplar tree, 6 ton per acre. Eucalyptus make 12 ton. Okay. So 1 ton is 2,000 pound or 907 kilogram. So 1 hectare is 2.47 acre. We want to convert the unit. So that's the yield of this crop. So a lot of those you can make in a marginal land. So let's look at ethanol calculation from these lignocellulosic. Okay, so weight of biomass, which is in tonnage, multiplied by 80. That's based on your research calculation. How many gallons ethanol will 6 tons of biomass produce? 6 times 80, because from the research that's what we found. You can make 480 gallons of ethanol from 1 ton of those crops that I mentioned. Okay, 480 gallons. Okay. Then we have cellulosic ethanol biorefinery concept. Look like that. We went through yesterday the same concept here. So you're going to have a biomass come in here. You handle the biomass, do the pre-treatment, add your enzyme, get your cellulose, hemicellulose come out, get your glucose, and ferment them, and you get ethanol recovery. Ethanol goes for market, and lignin is separated, and lignin can be utilized for fiberboard and other product you can use. And the hemicellulose is your pentosic sugar, goes to the fermentation. So you got to go through this pre-treatment process and enzymatic saccharification process before it goes to fermentation. Up to this is different compared to 1G, and 2G is these steps are added, and this is all the same with 1G. Okay. So that's the structure of different sugar. Polysaccharide is starch and cellulose, hemicellulose, and then you have disaccharides, and then you have monosaccharides, simple sugar, and the difference of 6-carbon, 5-carbon sugar in this cellulosic fiber. Okay, so all these sugars are present: fructose, galactose, glucose, mannose, arabinose, xylose. All of them are present in the plant crop that you can make ethanol off of it. So carbohydrates, when you look at it, various products you make out of this. Not only ethanol, you can make succinic acid, lactic acid, solvent like acetone, furan, glycerol, hydroxymethyl furfural, levonolic acid. You can see the list go on and on, right? Those are fine chemicals, high value chemicals it sells for profit. And you have fuels, ethanol, butanol, and biohydrocarbons, and then you get oligomers and you get oligosaccharides. And the lignin can be processed, separated and processed. You can do thermochemical conversion to make gasification, pyrolysis to make a lot of product come out of that. Then monomeric, you can make these simple molecules, lignin, basically phenolic compound. And then you make a lot of those polymeric product like cardboard, ceiling tiles, papers, all that you can make out of that. So everything is used up here. Okay. So let's switch to oil-based feedstock. I'm doing by time. Okay. Am I going too slow? Time is okay. I can speed up if you want. Okay. So let's look at. So we talked about ethanol. Now we're switching to diesel, biodiesel. Okay. So oil is extracted from seeds, fruits, nuts. Trans-esterification process is how you get your diesel. These are our feedstock: soybean, rapeseed oil, palm oil, sunflower oil, jatropha, or can be your feedstock. Global vegetable oil production is 170 million metric tons per year. Soybean is 45 million metric tons. Rapeseed is 26 million metric tons. Palm oil 59. Palm kernel oil 7 million metric tons. That's the world production of these particular oil seed crops. So that's how soybean crop look like. Soybean is in warm season we grow them. It's a leguminous plant, and it contains 21% oil. Major soybean producing countries are U.S., Brazil, and Argentina. So U.S. produces 31.5% of global soybean production. In the U.S., we use soybean as for biodiesel. So most of it for food, some of it go for biodiesel feedstock in the U.S. Rapeseed If you look at rapeseed data, that's how rapeseed look like. It's in India we produce rapeseed, annual oil crop, usually grown in temperate region, contains 45% oil. Major rapeseed producing countries are EU countries, European Union, Canada, China and India. With 10% world market we produce. In Europe, rapeseed is a major feedstock for biodiesel. So in US it's soybean, in Europe it's rapeseed. Palm oil, major producers Indonesia, Malaysia, is a perennial tree. Once you plant them, it stays for 30, 40 years. You can get the fruit every year. So it's a perennial crop. So 30 months and it can go up to 30 years. You can grow them. So the oil comes in this part of the crop. We call that flesh and mesocarp and kernel oil. So that's where they extract the oil out of the palm. Okay. So let's look at some of those yield. Soybean per acre, you produce 1.23 ton per acre, 21% oil. If you convert that tonnage per acre, you can make 129 metric tons from 1 acre. And the production is US is 129 and the worldwide is 369. So rapeseed you can calculate. So we have the based on the oil content of each crop, you multiply by the tonnage. That's how the production per acre, how much is each crop is, and you can see the worldwide production of this. Okay, million tons of it we are looking at. So let's look at the biodiesel that come out of these oil seeds. So you need the weight of the seed multiply by the oil content of every seed. And here is the assumption. So 1 gallon of oil is 7.6 pounds by weight. 1 liter oil is 0.9 kilogram. So 1 gallon oil equals 0.9 gallon biodiesel. So 1 liter oil is 0.9 liter biodiesel. So based on oil content of the feedstock, how much oil is there. Okay. So let's plug in some examples, how much you can produce per acre. So how many gallons of biodiesel you can make from 1.23 tons, because that's the yield you get, 1.23 per acre of soybean. Okay, so multiply with that assumption we had, you can make 61 gallons, and then in terms of liter, you make 231 liter from 1 acre of soybean. Okay, so that's your yield you can calculate. So let's look at biodiesel refinery. We have the lipids compounds, the biological origin. These are water soluble but dissolve in organic solvents. The lipids include terpene, ester of fatty acids. Terpenes include a large number of hydrocarbons that are naturally present in many plants. Ester of fatty acids produced in plants and variety of microorganisms. Yesterday we talked about microbial lipids, same ester, or basically oleic acid, palmitic acid, all that. So ester of fatty acid, you can plant make them wax and triglycerides. Okay. So biodiesel refineries, you take your triglycerides, gets fats and oil, and get ester of glycerol and long chain fatty acid comes out of that, and plant derived triglycerides are typical oil. Many plant produce triglycerides in their seed that can be used to produce biodiesel. So microorganisms such as yeast, fungi and algae are also source of triglyceride, which is yesterday I talked about, right? Microbial lipids. Algae can also produce 60% of the body weight full of triglycerides and lipids. Okay? So the refinery, how it works, you take your seed, you get a mechanical pressing, you get your oil come out, use your solvent to extract it. The residual seed material become a seed cake or a meal for animal feed. Then higher viscosity and lower velocity of triglycerides compared to diesel fuel. Then you do the trans-esterification reaction and you get your biodiesel. Okay, So you go through these steps and you get your biodiesel product. The byproduct is your seed cake, which is a good animal feed. Okay. Transesterification we went through yesterday. You know combine with the methanol and catalyst, and you produce biodiesel and also glycerin as your byproduct. Okay, glycerol. So one molecule of triglyceride reacts with 3 molecules of methanol to produce 1 molecule of glycerol and 3 molecules of biodiesel. That's your mass balance. Biodiesel is also known as FAME, fatty acid methyl ester for short. So that's your chemical reaction. You got this triglycerides, you get your methanol, you add your catalyst, and you get your fatty acid methyl ester, and you get glycerol is an end product. That's your biodiesel right there. So if you look at it, that's these 3 fatty acid triglyceride that converted into your biodiesel. So from 1 molecule, you can make 3 molecules of biodiesel. 1 molecule of triglyceride, you make 3 molecules of biodiesel. So to schematically, that's how it works. You get your biodiesel refinery process, you get your feedstock. The feedstock goes in their extraction process, and it goes into your transesterification, the oil that comes off it. Put your methanol and catalyst, and you phase separation, and you get your biodiesel as your main product, and then you get your glycerol come out, and as a glycerin you can make out of that. And then your cake comes out, you can use them for other purposes, and centrifugation, algal cultivation, a lot of things you can do that. Then you have, this is going to be a lot of source for protein for animal feed. Glycerol is used for pharmaceutical and personal care product, and also in some food industry. Okay. So let's look at some stoichiometry, right? 100 pounds of oil plus 10 pounds of methanol is what you need to make a biodiesel. That gives you 100 pounds FAME, 10 pounds of glycerin when you make the product. So that's your yield from your chemical reaction. So some of the facts about this biodiesel, alcohol to oil molar ratio is 6 to 1. The higher result is, maximum yield is 98%. This reaction time is 30 to 45 minutes. Okay. Alkaline catalyst is 0.5 to 1% by weight. Reaction temperature is 60 to 70 degrees. Acid catalyst used for feedstock with high free fatty acids. Example, cooking oil and animal fat, you need little different ratio. Alkaline reacts with your fatty acid, you can make your soap and other thing material from that. Okay, so that's some of the facts about how much you need in your ratio in your feedstock, what is coming in. Okay. So switch to the last one on anaerobic digestion biorefinery concept. It's anaerobic digestion, again we went through yesterday. It's a biological process that breaks down organic material into under anaerobic condition into methane and carbon dioxide. So anaerobic process occurs naturally. Example is in the cow, and in our large intestine we do the anaerobic reaction, and in the wetlands and in the sediments it all naturally happens. Okay. So in digester, this is what's going on. You have your feed comes in from manure or lignocellulosic crop as a co-digestion. You digest them, you get your biogas, you clean the biogas, and you can use the biogas for various purposes, transportation, natural gas grid. Then you can also, without going through cleaning process, you can send it for cooking purposes, and you can also use cogeneration to make electricity, run your electricity generator. And then you get your digestate. Digestate can be separated into solid and liquid. Liquid can go into foams, and then the other dry material can be used to make gardening, spreading, and other purpose. So if you look at it, nothing is wasted here. Everything is used up. That's your biorefinery concept. Okay? So why anaerobic digestion is a clean and renewable energy source. It can make every year without destroying the environment because it comes from the waste material like manure and lignocellulosic feedstock. It's very diverse application. You can produce either stationary power to make stationary cooking pot, or you can use it for transportation fuel. Very versatile, capable of handling diverse feedstock. So you can put a lot of stuff in the anaerobic digester. It's a very mature technology. We figured out the microbiology, biochemistry, mass balance. We know everything what's going on in the digester. Yesterday I gave you all the list of biochemical reaction and bacteria involved in the anaerobic digestion process. It's ideal for remote location in the villages as an energy source. It's potential for greenhouse gas emission reduction. Okay, it's very effective in waste remediation also. So these are some of the reasons for anaerobic digestion process to be widely used in the world. So we can use a small scale in the home that we in India is very common, like we call gobar gas. In my hometown, some of the people have in the villages. The cow dung is put in the cement anaerobic tank, and just put water. They don't have any sophisticated thing. You put the manure and add bucket of water, mix it, and open into the digester. Then 24 hours later you get your gas, and that goes directly into cooking, right? So that happens right in remote villages, and then the digestate is used for farming. Whatever comes out of that goes into their farming operations. Okay, so that's in example in Cambodia. The biorefinery concept here is schematics that shows how you can use everything that comes out of the digester. So here is your feedstock, biomass or manure goes into your bioreactor. You produce your biogas and goes into your heat and power directly, or you could electricity grid. Then you have the digestate that can be go through torrefication process. You can make all those syngas and other things, biochar. Biochar can be used for land application, make biopolymer and a lot of other stuff you can make. And then the biomass can be used as dried and used as dry feed for heat and power. Okay, so if you look at it, everything is used. The CO2 separated, CO2 can be also purified and used for your carbonated water drink or making dry ice. So CO2 is, instead of letting it out, you can capture CO2 and produce some product out of that. So that's how a digestate look like. It's a residue produced after anaerobic digestion of biodegradable material. It's consists of a mixture of microbial biomass and undigested material, lot of nutrient in it, a lot of nitrogen, phosphorus, very good for crop production. Okay? So you can densify it, and this will be a good heating source. You can burn it, or you can use other purposes. So that's a different form of digestate. That's how fermentation residue look like. When you clean up the tank after several years, all the digestate comes out. And when you dry them, that's how after moisture is lost, it's really dry. Okay? And then the commonly used, instead of drying, the sludge can be directly applied in the farm. That's called fertigation. That's commonly used in US and Brazil. Then you can also use co-composting for your dry material that comes out of it. So you can put in compost, and the self-heating compost heats up. So all the pathogens are killed, and you can use that composting to make as a soil conditioner to put back in the soil. In the different ratio you mix it, and then you can use them. Right. So these are various use for your digestate that comes out of anaerobic digester. effluent directly used as for irrigation, spray, and you can also make a high value fertilizer called struvite. Struvite is from all the elements that is in the digestate, and you can make struvite. And you can also use this for algal production. The digestate could be used as a feedstock for algal production. So this is one of the example of microalgae production comes directly coming from big anaerobic digester effluent, and algae use that as a nutrient source. They multiply really fast. This is in Hawaii. Okay. This is how a struvite is made. Take the digestate, and basically it's all the leftover chemicals in your digestate, which is ammonia, magnesium phosphate. That is called struvite. That's your fertilizer. You can apply. It's a slow release fertilizer. It's really nice to apply. So just to show an example of the digestate use in fertilization in the farm. The solids also can be used as animal bedding. If you have a lot of animal producing farm, you can compost them. You can make fuel pellets. You can make fiber and make fiber board, or combined with plastic make a composite. So that's an example of digestate for animal bedding. This is your fuel pellets. You can make pellets out of it, and then you make a fiber board out of that. So a lot of product comes out of that, right? So I'm going to end here. The work was in collaboration with Dr. Samir Kanal, a professor in University of Hawaii. So we collaborate together. Okay, I'll stop here and I'll take questions. Okay. Yeah.
Open to the question session.
Yeah, over there. There is a micro.
Thank you for a very nice talk, sir. Just wanted to ask about the sugar-based platforms.
Yeah.
You mentioned about sugar-based platforms. Sir, I was interested in the wastewater which they were releasing. So after the advent of this zero liquid discharge policy, every industry has to manage their wastewater, particularly about reuse and recycle those wastewater.
Mm-hmm.
So anything you can suggest for this wastewater, particularly from these sugar-based biorefineries, or how we can manage or how they can utilize it?
You're talking about from effluent coming out of the sugar factory?
Yes.
Yeah, sugar factory, the effluent still has a lot of sugar in it, residue in it. So people treat them as wastewater, so you have to treat them. But it'll be a very good feedstock for algal production. So if you have a land available, you pump it in there, let the algae take over. Very good feed. It's a heterotrophic algae, because heterotrophic algae need organic carbon as a food source. That's one way of doing it without spending money. And it's not worth it to take the sugar out because there's a lot of water in it. So right off the top, that's one thing coming to mind. You can make use of
Sir,
algae.
anything wastewater could be utilized for this energy recovery or something? We
Wastewater
can divert it towards energy
from the
recovery?
sugar factory,
Yes.
because the volume of wastewater is so high. The gallons, I mean, it's really a lot of water they use in the sugar factory. So I don't think it's economically feasible for using that wastewater for something else. Yeah.
Sir,
Yeah.
actually, the main reason for this question was that these industries are releasing effluent without treating.
Oh yeah.
So it becomes a problem of eutrophication because of high nutrient content in this.
Yeah, exactly. That without treatment, you're gonna have a high BOD, COD, then you're gonna have a fish kill and all that stuff happen. Yeah. I don't have an answer for that. There's a lot of wastewater coming out. Yeah. I think algae production will be one idea. Comes out of my head. Okay.
Okay, thank you, sir.
Yeah. Yeah. They can talk or they can type in. Yeah.
Sir,
Me too.
sir, I have one question.
Okay.
Good morning, sir. Very wonderful presentation about biorefinery. Very good concept of
okay.
biorefinery. I am Dr. Bharati from Biotechnology Department, Vishra Engineering College, Bagalkote. Sir, I have one question. Like in molasses, we
Yeah.
use the sucrose for ethanol production. Right, sir? Only sucrose will be used from the molasses
Yeah.
for the ethanol conversion.
Ma'am, little bit loudly, ma'am. Your voice is
Ah,
not audible.
Not audible.
Please.
Yeah. 1 minute, sir. Yes. Now, sir. Yeah. Hello. Am I audible?
Yeah, now it's audible.
Okay. Apart from the sucrose, which we use it for ethanol production from molasses, as per my knowledge, what will be the other sugars? Is there any other sugars which are there in the molasses? Yes, yes, sir. What is that vinasse, sir? Is it a sugar? That what we call spent wash? Is it a spent wash, sir?
Yeah, we call it vinasse. Yeah, exactly.
Okay.
That mostly in Brazil they use it in the farm as a fertilizer. It just goes into the farm.
Oh. And related to this algae, which you suggested to grow it in wastewater, actually we tried in the sugarcane means sugar industry process wastewater, not distillery wastewater. Process wastewater, we could grow algae directly, sir. That is that algae which we can suggest them to use it for biogas production where they have already the biogas production. So that project we did one project, a small project we did it in our college, sir. And coming to biodiesel, so what you suggested is free fatty acids which we have a more FFA, that is more than 5% FFA. So we should go for acid treatment. Is that any possible? Okay, that is fine. We will remove that layer that is using the acid. So that waste, what we can do, sir? Can we use it for some other purpose? Okay. Okay, sir. Thank you, sir. Thank you so much.
The digester from the anaerobic digestion wastewater is directly used for the agriculture without any further treatment because the wastewater contain pathogens and heavy metals also.
Yeah. So the anaerobic digester, if you are manure-based digester, it can go directly into the farm without any process because it's come out of the cow manure. Manure is not a problem. The pathogen is not a problem in anaerobic digester because under anaerobic condition, most pathogens get killed. And most of the pathogens are aerobic. Some of the anaerobes cannot compete with the bacteria already well established in anaerobic digester. So very less pathogen, very minimum pathogen. So we don't worry about pathogen in the digest state. Okay. Heavy metal is based on what is in your feedstock, what goes into the digester. The heavy metal is an issue, but based on agriculture feedstock, like co-digestion with manure, I don't have any problem with heavy metals. Okay, if you have co-digestion with some other factory wastewater going into a digester that has heavy metal in it, then that will be a problem. you cannot use it for agriculture. Yeah. Yes. Okay. Any other questions? No, not there? Okay. All right. Thank you. Thank you very much.
So we'll be back after a short break.